So good afternoon, everyone. Welcome to the last session of today. We have 5 more presentations coming, 2 online and 3 in person. My name is Berend Vreugdenhil. I'm the task lead of task 33 on biomass gasification.
And good afternoon, everyone. Thank you for being with us and for the people here online joining us since this morning. So I'm Chourouk. I'm also from the Task 33 Gasification, and we will talk about the promising development in bioenergy concepts in this session. So our first speaker is Marion Maheut. She's joining us online. So can we just, so Marion is the project manager at ENGIE, working on a gasification process and production of sustainable fuels like methane, biomethane, and biofuels. Hello, Marion. We don't hear you, so we still don't hear Marion. Can you? Yeah, a little bit. Try again? Yeah, okay, good.
Hello, everyone. Can you hear me well?
Yes. Can we also have the presentation, maybe?
Yeah.
So you can go, Marion.
Okay. So hello, everyone. Do you see the full screen, or do you see the thing at the bottom or at the top?
It's okay. We already have a presentation. Yeah.
Okay. So so once again, hello, everyone. I'm Marion Maheut. I'm from the research center of ENGIE called the Lab Cryogen. And I will talk about the diversification of applications downstream pyrogasification. So gasification is a thermochemical conversion of solid biomass and residues into a product gas, also called syngas. So this syngas is the basis of a broad spectrum of valuable products and application, because it's a very good chemical precursor, as it contains hydrogen and also carbon monoxide, carbon dioxide. So syngas can be either used for direct heat and power generation, or upgrading it to green gas or liquid products. So the product spectrum includes hydrogen, synthetic natural gas or biomethane, liquid transportation fuels such as biodiesel, kerosene, and finally also chemicals and energy carriers. So pyrogasification is a very versatile technology, as it can be applied in different market segments and also react to market changes. So it offers powerful pathways toward a sustainable energy transition. So you can see here the different steps to these different products, and I just put some numbers about the yield in terms of biomass or residues to fuel, depending on the application. Gasification is a kind of super ordinate term, but a wide variety of different gasification technologies are available on the market. And the selection of the technology depends on the number of different factors. And of these, the most prominent are the selection of the feedstock and also the end product and the scale of production. So this table gives most common or demonstrated application for each technologies, even if there are some developments to diversify the application for each one. So for fixed bed gasification, either updraft or downdraft, is typically used for small-scale application in the kilowatt scale range to produce heat and power. Fluidized bed, either single bed or dual bed, are used in medium to large-scale application ranging from around 1 to 100 megawatts. So fluidized bed gasification enables more complex biorefinery processes with downstream gas upgrading equipment, and also can produce, for instance, SNG, hydrogen, chemicals, liquid fuels. So the same is true for untrained flow gasification, which is typically applied at even larger scale, above 100 megawatts. And so they are more particularly suitable for liquid fuels and chemicals because they produce a high hydrogen content, and also because there is a kind of economy of scale. So that's more suitable to go to higher price end products. Plasma gasifier operates by gasifying the feedstock in a plasma generated by a high energy electric arc. So they produce a high quality syngas, but they also consume more power than other technologies, which could impact the carbon footprint of the final product, depending on the carbon content of the power, and so the country where the technology is used. And finally, the two stages process consists generally in a first step of pyrolysis and a second step gasifying the char produced during the first step. And the gasification technology could be one of those mentioned above. So the capacity, the application, and the advantage and disadvantage of this two-stage processes highly depend on the gasification used. So among these, ENGIE is testing the dual fluidized bed gasification, also called FICFB, for fast internally circulating fluidized bed. So I will give you different examples of ENGIE Lab Cryogen demonstration project for different applications. So the main one, I would say, or the historical one, is around the Gaia platform. So ENGIE has built and now still operates this demonstration plant. So it's a cutting-edge R&D and also pre-industrial scale, because it's highly automatized demonstration plant to produce bio or low carbon fuels from biomass and waste pyrogasification. It's located close to Lyon, so some of you already visited this platform, and tomorrow some of you will visit it. So you have several areas, but the technological area is here, and you have different, so it covers the overall process chain from biomass reception, storage, treatment, and also the conversion, gasification, syngas cleaning, and methanation. And we have lots of sensors, analyzers in order to optimize everything at each step. And we also can welcome new technologies to diversify the application and also the technologies along the value chain. So the Gaia project was co-funded by ATEE within the framework of the Call for Expression for Interest and the second generation biofuel demonstrator fund. It gathered 11 partners, including, you can see here, it was coordinated by ENGIE, and the objective was to demonstrate the bio-SNG production from biomass gasification at the beginning, and at the end of the project, we also performed some tests on waste, such as refuse-derived fuel. You see the timeline on the right. So basically, we started the project in 2010, and we started the operation during 2018. And we are still operating the Gaia platform, even if the project with ADEM ended at the end of 2021. Here are some main results. So for the technical parts, we have demonstrated the overall process chain. And we have performed more than 150 tests. We have performed long duration tests. So we are confident in this process chain. Also, we decrease the production cost compared to the state of the art, thanks to several innovation and more than 10 patents. So compared to the state of the art, we decreased by 30% the capex, and also we decreased the feedstock supply costs by using lower cost feedstock and waste. And also we confirm that this pathway has an environmental benefit. For the biomass conversion, you see the number which was assessed and validated by an external panel of experts, and we are doing the same for the waste valorization. So the Gaia project helps to go from the lab concept, and right now we are at industrialization step. So the first commercial plant will be the Salamander project. The capacity of this plant foreseen is 20 megawatts, and you can see here first sketch of the commercial project. So this project will be based in the harbor of Le Havre in Normandy. So here are some figures about this project. So basically, we will produce 170 gigawatt hour of SNG and also 11 kiloton per year of synthetic liquefied natural gas for heavy and maritime transport, and also for intensive industries around there. And we will co-produce also 40 gigawatt hour of renewable heat that can be used either for industries in a form of steam, and also for urban networks. And we want to valorize 70,000 tons of a year of non-recyclable waste, mainly wood waste and solid recovered fuels. And beyond that, also we want to create synergies and increase the amount of carbon contained into the initial feedstock in final product. So through the Salamander project, we will produce this low carbon synthetic natural gas, but we will use the CO2 capture from Salamander to produce e-kerosene as part of another project from ENGIE called France Kerosene. So the Gaia platform is still operating, and we are very open, and we collaborate with partners also at European level in order to continue to validate innovative solutions, either for syngas cleaning, catalyst, syngas conversion technologies, and also SNG upgrading technologies. We want to pursue our feedstock diversification. In particular, we want to address more and more non-recyclable waste. And also we want to diversify also the application. So basically we would like to go to hydrogen or co-production of hydrogen and methane. And also I will present you right now a project, a brand new project who was granted this year, coordinated by TNO, in which we are a partner. So Butterfly comes from biomass utilized to the extended portfolio of renewable fuels with large yields. So the objective of the project, who was launched in July this year, is to co-produce renewable dimethyl ether and SNG, and applying, for instance, hydrogen produced from electrolysis in order to produce these two products at tunable ratio by converting the CO2 coming from the process chain. So we want to diversify also the feedstock. We will address lignocellulosic biomass, industrial waste, and also upgrading wet organic residues. We will valorize then the RDME and SNG for off-grid energy supply, maritime and heavy-duty transportation, and also for steel industry. So the concept is we will use part of the Gaia process chain with the indirect gasification, the syngas cleaning, and also the methanation. But within this process, we will integrate a new technology brought by TNO called SENMES, which is a sorption enhanced DME synthesis reactor. And so we will co-produce DME and SNG, and at tunable ratio, depending on the demand. Either, for instance, in winter, if we need more SNG to produce heat, or in another season, or for any reason. That's the goal of this project, to study what's the best optimum in terms of in technical, economic, and environmental aspects. So the goals are to improve biomass to fuel conversion efficiency by 15%. We will achieve up to 97% of carbon efficiency. And also we will optimize the synergy of RDME and SNG production. Here you can see the different partners of this project. So TNO is coordinating, and you see that also Politecnico of Milano is part of it. Yeah, lots of partners that you can see here. Either for the feedstock supply, and also logistics, for the conversion demonstration, and also for the final application. For instance, for RDME, DMETA will study, for instance, the DME market, and some of the partners will also study the DME application in industry, for instance. So thank you for your attention.
Thank you, Marion, for your presentation. Very clear. Maybe we'll take one or two questions. Yes.
Thank you. Jean-Philippe Héraud from Maxence. Thank you very much for this presentation. Very interesting, very clear, and congratulations for the results of the demo plant. One little question, because I probably misunderstood the point, or maybe you can clarify. At the very beginning, you introduced a different type of gasification process, indicating that the type you selected goes for medium-sized capacity. And I see now that you are studying a DME market, which is a liquid fuel market, which is a large market. So is it fully compatible, or at least for such application, this technology is the best one according to you?
Yeah, indirect gasification can be suitable, but that's also the aim of the project, to see how we can best optimize the valorization of the syngas between the SENMES technology, who will produce RDME, and also the SNG production from the methanation. And for instance, part of the concept is to maximize the carbon content. And so, for instance, valorizing the off-gas coming from the RDME reactor into the methanation. So that's the goal of the project. But yes, if we go through this project, is because we think that it can be suitable. Yeah.
Do we have another question from the room or online people? Yeah, maybe the.
Hello, Nicolas Bijon from Solagro. Thank you for the presentation. It's very interesting. I had a question about the use of refuse-derived fuel, both in the Gaia process and in the future salamander process, and several questions about that. First, did you achieve sufficient cleaning of the biomethane for injection in the gas network in Gaia? And is it a use that you plan to pursue with the salamander project, or are you going to take RDF there? And if so, isn't there isn't the RED II directive from Europe a problem for this type of fuel because part of this is not biogenic?
Okay, so 3 questions. Yes. So the first one is, so basically, if you guarantee a very clean syngas at the end of the syngas cleaning step, then the methanation part won't create any new pollutants. So we have a very clean, so it's not because we have biomass or waste at the beginning of the process that the final SNG quality will change, because the methanation is a catalytic process. So we have to do the main job before the methanation. And yes, we have performed also exhaustive analysis on the final SNG coming from SRF or RDF and also waste wood. And we see that there isn't any change in terms of quality compared to biomass. So the second question was about the local supply of around Salamand, right?
Yes.
Okay, so yeah, the I cannot give the name or suppliers, but yes, the idea is to supply close to the Salamand future field, so it will be local. And in terms of environmental impact, that's a very, very good question. And that's the idea of the studies we are doing right now. When I talk about the carbon score for biomass, I was mentioning that we are performing also life cycle analysis for waste such as refuse-derived fuel in such process. And indeed, the biogenic fraction from the initial feedstock has a high impact. So that's a compromise we are looking right now in order to fit with the sustainable threshold. So it won't be, for instance, 100% of RDF with, if you take 100% RDF with lower, with a biogenic fraction lower than 50%, of course, you will never reach the sustainable threshold. So that's a compromise to find. With over mixing with over biogenic residues.
Thank you, Marion. And thank you also for all the, another question?
Yes, we have an online question. What is the size of the butterfly project?
So the size, so basically we will use the size of the Gaia plant. So the gasifier is around 600, 700 kilowatts input. And then we produce around 40, 50 kilowatts of SNG. And in terms of DME, it will be several kilogram per hour. So for the overall project, if I remember well,
750.
several, yeah, I don't remember exactly how many hours, but yeah.
And do we have time for a last question?
Go ahead.
Okay, so for one online question, for the biomass input, will you prefer fermentable fraction or more woody biomass, lignocellulosic biomass?
I think it was already presented.
Yeah.
Yeah. So yeah, more like woody or yeah, fermentable fraction, I think are better for biogenic pathway, biological pathway. But we are also studying difficult wet residues, as I mentioned, as part of the butterfly project, by using, for instance, hydrothermal carbonization and something like that. So yeah, some difficult wet feedstock could be valorized into gasification, but they need pre-treatment before.
Thank you, Marion, and thanks also for all the ENGIE team that will assure tomorrow the visit of the Gaia plant for some of our participants.
So our next speaker is Joakim Lundgren. He is professor at Luleå University of Technology. Besides that, he has several other positions, but I think being the deputy director of CHES is probably an important one also for the presentation he's going to give. He's also the representative of Sweden in Task 33 and in charge of all our activities related to hydrogen production via gasification. The floor is yours.
Thank you very much, Berend, for the introduction, and thanks for letting me talk today. Very appreciated. I will discuss hydrogen, which is very hot, but not through power-based hydrogen production, but from biomass and gasification in particular. Somebody said today that AI is the flavor of the month. I would say that hydrogen is the flavor of the year. Definitely, it's extremely hot, and if you follow the news, there is simply large news on investments and projects, large ones, more or less every day. It's about hydrogen-driven trains, aircrafts, new steel plants that will be based on fossil-free hydrogen. I had to put in one of the news on Sweden, where steel making using fossil-free hydrogen is very, very interesting and hot. Now it seems like we're also planning for steel production in Canada using the same concept with DRI. So very, very hot, which also is reflected in several of the scenarios that is developed for the future. And of course, we already today use hydrogen for different purposes, mainly fossil-based hydrogen. But as you can see, the demand for hydrogen will grow more or less exponentially. Doesn't look much between 15 and 30, but it's close to the double, 75% in a quite short time period. And then later, more or less explode until 2050. It's a factor 10, more or less, during this time period. So I think there is a consensus that the majority of the production for a fossil-free hydrogen will most likely be electrolysis and power-based hydrogen. But I'm a little bit annoyed, if I should be honest, when you directly convert the demand for hydrogen, translates that to how much power you need by just dividing by 0.7. Completely forgetting that there are other technologies as well that can supply the hydrogen. I'm also a little bit skeptic to this color, different colors of hydrogen, and as you can see here, green hydrogen, it's electrolysis using wind, solar, and hydro or geothermal. Gasification is mentioned, but then it's black or brown when you use coal. So if you aim at using biomass, there is no color that fits very well. I would definitely count it as a green one, but it's a little bit unfortunate that it's overlooked. Biomass-based hydrogen in general. Today I will focus about my favorite technology, gasification. Which I simply think needs more attention. I will not say that this is the silver bullet technology, because it's most likely not. But it has very, very interesting technical benefits. For example, that it doesn't depend on the weather. It's not intermittent. You can produce it 24/7. Of course, it's fossil free. You can also do it in fairly large scale. Like I said, it's not a silver bullet. It's not either or electrolysis, but it can actually mitigate the power demand for electrolysis to some extent, at least. I think it would be valuable if you can replace or perhaps produce 10% of the demand for fossil-free hydrogen using biomass. That's a very good contribution. We also have extremely interesting process integration opportunities, and perhaps in particular if you talk about gasification. Integration of gasifiers in pulp mills, sawmills, maybe even in the steel plants, and especially when they are becoming fossil free. And not to forget that it's been mentioned several times today, that the opportunity to actually create negative emissions. So this is what I will focus on today. Marion presented this much better than I did. The technologies for gasification and the characteristics that it's very flexible in feedstock, but it's also very flexible on the final product side. So I will simply skip the technical things because Marion already done it. This is a very rough sketch of the process for producing hydrogen via gasification. I will not go into details here, but I think most of you are aware of the processes needed. You need to get rid of some nasty stuff that we don't want, like acid gases and sulfur and other contaminants like particles and stuff. And then you need to make the gas a little bit better by conditioning, and also remove the CO2, very important, and then purify it with, for example, PSA to get a high quality hydrogen stream. But important here, a very rough mass balance is that if you gasify 1 dry ton of biomass, you can produce around 100 kilograms of hydrogen. At the same time as you produce 15 to 20 kilograms of CO2 per kilograms of hydrogen. So this is very, very rough balances. And I will not focus on the technical things now on producing hydrogen. I will more focusing on economics, which I think is quite interesting actually. And I've used an IEA Bioenergy publication. I think there might be some, I don't know if there are some co-authors, but I know that people in this room has been involved in this report. I have here, because it doesn't include hydrogen in this report, but it's a relevant assumption to say that the production cost for methanol and methane via gasification will be roughly the same as gasification-based hydrogen. It won't differ that much. And in this report, they presented production cost for these commodities with different scenarios, one more higher costs and one lower cost. And I also took the freedom to extrapolate with different feedstock costs. I think the last time I checked feedstock cost for biomass wood chips, it was around 25, something like that, euros per megawatt hour. Competing with fossil-based hydrogen is not easy. This is rough cost for hydrogen produced today via steam methane reforming, somewhere around €1 per kilo up to maybe €2 per kilo, somewhere there. And what we can see is that at the current conditions, it will be very difficult for biomass to compete with this. But I continue to calculate. Remember that we also get the CO2 stream that might have a value. Here I have assumed that, of course, if we capture and store the CO2 from the plant, we create negative emissions. Negative emissions will have a monetary value. And here I assumed, this is based on several studies, that it's foreseen to have a value around 100 euros per ton of CO2 if we can bury it underground. I also assume that the cost for CO2 transport and storage will be around 50 euros per ton of CO2, which means that if this is done, you can have a net credit subsidizing the production cost of hydrogen by roughly 50 euros per ton of CO2 produced. And using the numbers that I presented before, it means that we can push down the production cost quite significantly. I have now compared with SMR coupled with CCS to make it a little bit more comparable. And what we can see then is that, well, it's becoming improved. It will still, following the high cost scenario, it will be difficult. But with the low cost scenario, according to the IEA report, it's actually with feedstock prices that we have today, it starts to become feasible. Even though I don't think it's perhaps extremely fair to compare these two costs. You recognize this guy? Some of you might. He has stopped playing soccer, unfortunately for Sweden. But this is Zlatan Ibrahimovic. He was a fairly good player. I mean, he was in PSG, he was in Milan, Inter, Manchester United. He was a very good football player, perhaps the best we have had in Sweden. This is also Zlatan, but Zlatan, 8 years old. And Zlatan, 8 years old, he would not be able to play in PSG or in Milan or Manchester United. Maybe. I mean, it has taken a lot of support, practice, training in order to become this Zlatan. And it's exactly the same, not only with green hydrogen, but green technologies in general. They need support before they can compete with fossil alternatives. So that's, I think, it's an important message. So what about competing with power-based hydrogen? Well, according to my calculation, this is also from IEA Hydrogen, on the estimated cost for solar and wind-based hydrogen 2040 to 2050. And if I put in my estimations of gasification-based hydrogen, it's somewhere around in this span, $2 to $3 per kilogram. And what you can see here is that in the Northern Hemisphere, it's competitive also to power-based hydrogen. So I think this is actually quite promising also from an economic point of view. We have also calculated the CO2 abatement cost for a large number of transportation fuels, including aviation fuels. And I will not go into detail here, but this is the hydrogen cases. And as you can see that they are comparable with most other biofuels and electrofuels and bioelectrofuels. And zooming in, I just want to show that according to our assumptions made, the CO2 reduction cost is actually lower for the gasification cases than for the electrolysis cases. This is in Swedish crowns, so you have to divide by, well, almost 12 nowadays, so it's to get euros. But so also from this perspective, it's actually interesting. To summarize, I think that I know that gasification brings many attractive technical benefits, environmental benefits, and also, as I showed, economic benefits compared to many other. Like I said, it's also difficult. Sorry. How do we go? This one. It is difficult to compete with fossil-based hydrogen today. But I also think that I didn't mention that the development of CCUS in other applications than gasification will sooner or later lead to lower capital cost, which means that also the gasification will benefit from that and become more competitive. Perhaps also it's possible to apply this in smaller scales. So this is very good for gasification. According to my estimates, we see that both production cost for biomass-based hydrogen and CO2 abatement costs might actually be lower than the cost for power-based hydrogen, especially in the Northern Hemisphere, many regions. So it's not a silver bullet, but it definitely deserves more attention. So this is where I will stop, and thank you very much for your attention.
Thank you, Joakim. It's time for maybe one or two short questions. Yes.
Hi, thank you for your presentation. Important to mention also that Zlatan played for Ajax.
Oh, yeah.
So I'm from the Netherlands, and the Dutch government has decided, I think a year ago already, to not stimulate or subsidize hydrogen from biogenic sources due to the low availability of biomass in the Netherlands, and we need the carbon molecules for something else. So how do you feel about that position already with the Zlatan example in mind?
First of all, I think the support should be technology neutral. I think the market should somehow control that. I'm convinced that one technology and one feedstock that is not suitable in one country might be in another. I mean, the situation for example, forest biomass is completely different in Sweden than it is in the Netherlands. So I don't know if that was an indication of the answer, what I think. Yeah. There
was one question, yes?
Yeah, thank you. Super presentation. I was just wondering, in these kind of comparisons, your opportunity costs are ignored. So, I mean, as Bas also said, there are other ways to utilize the biomass and so on. And maybe there's a high willingness to pay for that in aviation, for instance. How would you, or what do you think would speak against producing hydrogen? Like,
I mean, it's not. I mean, we have discussed that today, that you should be careful with the carbon in the biomass. It's valuable, and here in this case, you just perhaps store it underground, making not use of the carbon. That might not be the best solution. I'm not claiming that this is it, but like I said, it deserves more analysis and assessments and more attention. I'm 100% that you can find cases where other production methods is better, but I also think that there is a difference depending on where you are, what you need, and if you have a nice business case using this concept, go for it. You might not have a business case in another geographical area, but I'm just a little bit hesitant trying to find these best general optimal solutions because they will be different.
Okay, thank you. I think that's the last question. So thank you, Joakim.
Thank you.
We go to the next speaker.
Thank you, Joakim. So the next speaker would be me with Frédéric Thiollier from the group IDEA. Frédéric is the Deputy Director of Bulk Logistics of the group, and we will talk about the synergies between different bioenergy technologies. Like earlier we talked about gasifications, hydrothermal gasifications, and anaerobic digestion. So next slide, please. Thank you. So just to see a few words, it will be difficult to do a better presentation after the super presentation of Joakim. So first, what we can say is that tomorrow we need different technologies because we need energy, and we have like biomass or electricity supplies. We have different type of technologies that can be used, and in this project, the project of Barillais Eco-Parc, we have 3 different plants. Each one is based on a technology. The first one is the anaerobic digestion, and we use agriculture and manure feedstocks, and it's the fermentable feedstocks that we use for this production. The second plant would be a gasification plant, like the High Move project with gasification plant, and we will use woody biomass waste as a feedstocks. And the third plant would be, if we get the right support, the first hydrothermal gasification plant, and we will use some sewage sludge feedstocks. So this project is an example of what we can make in one project, in one place, what we can make with different feedstocks, with a complementarity between those feedstocks. I will maybe explain what is anaerobic digestion, gasification. You already had the explanation of Marion and Joakim. So anaerobic digestion, we put the feedstocks, the fermentable feedstocks, in a fosse, and it will just give us what we call biogas. Biogas is a combination of methane and CO2. And if we clean this biogas, we will get methane that we can inject into the grid, and we also have the CO2. For gasification, it's probably the same thing. We have a syngas, which is a combination of CO2, not a lot of methane, but we do a methanation to upgrade the syngas. And after that, you have methane you will inject also into the grid, and you will have also the production of CO2. And for the hydrothermal gasifications, the same things. You will get a syngas, which is a combination of same molecules, CO, hydrogen, and a lot of methane in this case. You will just clean it, upgrade it, and you get methane. You inject it into the grid, and also you have CO2. So in this project, basically, the main products will be methane and CO2, and we can use it like for industrial use, for heat. We can also store it into the grid. So just to conclude about this introduction, in France, we have, as mentioned this morning, ADEME worked on different scenarios, the energy transition scenario for 2050. And as we can see in this scheme, we have different ways to get to the net zero approach. And in this different case scenario, we have to use anaerobic digestion, gasification, and hydrothermal gasifications to get to our target. So now we will see the example of Barillais Eco-Parc project with Frédéric.
Okay, thank you. First of all, forgive my bad French accent. I'd like to say first, as part of our strategy, we aim to provide a greener logistic services. And the supply, yes, I will. And the supply of renewable electricity and renewable gas, I think is a key factor of our success. You can see the plant 50 years ago. It was a chemical fertilizer plant. Producing ammonium nitrate. The site is located in Montoire de Bretagne, in Loire-Atlantique. And this plant has been deconstructed and has been cleared. And we bought the site in 2029. And there are 20 hectares, and 6 hectares are available for the project. What is important for this site is near the harbor of Montoire and Saint-Nazaire, and there is two gas network next to the site. The main gas network for transport and for the distribution. So it's an advantage for us. We have reclaimed a warehouse. You can see in the middle of the slide with asbestos roof. So we changed the roof and took the opportunity to install 800 kilowatt photovoltaics panel. And we start to work on the anaerobic digestion unit with Volve biomass, and we set up a storage platform to recycle wood waste. And as I said, we are near the harbor, and we have a railway platform on the site. So we have the possibility to offer a multimodal way of transport for our clients. 2025, the aim of the site. You can see the aim on this site with various projects. And sorry, the light, yes. With various projects completed or in progress. Sebest is completed. It's an anaerobic digestion unit. iMove is in progress. It's a gasification project. Gamma is in project as well. It's thermal gasification. We planted half an hectare of trees, and we go on to install photovoltaic panels to supply collective consumption. So the anaerobic digestion unit, you can see the photo of the unit, has been commissioning in last year in April 2022. The shareholders are ENGIE Bios, La Carène. La Carène is it's public. It's the municipality around the site, and my company IDEA. You noticed it's a mix of public and private organization. Inputs, it's of course organic, and for 40% is from agricultural waste, and 60% for agri-wood waste. What is important to retain? It's a local unit, local project. For example, the input come from a radius of 20 kilometers around the site, around the unit. And for the digestate recovery returning to soil, there are 12 farm operation, and they are going to a radius of 25 kilometers around the unit. We are authorized to process 28,000 tons each year and that will produce 21 gigawatt hour for each year. It's about the flow rate is about 250 cubic meter per hour. Yes. Yes, and for the digestate recovery, it's around 25,000 tons each year. And at the end of the year, we will be commissioning an CO2 recovery unit, and this liquefied CO2 will be used in a greenhouse to grow vegetables. And for the anaerobic digestion unit, it's about 500 tons of CO2 equivalent. It allows to avoid 5,000 tons of CO2 equivalent. The next project is a gasification project. Do you know that 3 million tons per year of industrial wood waste in France, only 50% of this waste are valorized in France for wood, and the rest is buried in landfill. We see that this morning several times, but it's important to repeat it. France is aiming for neutrality carbon in 2015 with strong objective on the waste recovery rates. So we decided to create iMove. It's a joint venture with IREMIA on my company. IREMIA is a little company specialized in treatment, in wood treatment. The aim of the unit is to the input is wood waste, and it's about 20,000 tons each year. Okay, I will not focus on the process. Just I will say it's sorry. Okay. It's a high temperature process that breaks down the molecule, and we obtain methane, hydrogen, carbon monoxide, and carbon dioxide. We clean the gas, and we mixed the molecule together to obtain methane. But if we want, we can obtain hydrogen with another process. We are still working on engineering process, and we have particularly selected the supplier, and the flow rate will be about 600 cubic meter per hour, and it's about 14 gigawatt per year. The next, is hydrothermal gasification unit called Gamma. Gamma is a consortium with GRT. GRT is an operator of the main network, gas network. Luleå is a main actor in the engineering process in HTG technology, and he works with the KIT in Dutchland. Nevesus help us in plant operation, and Cerema help us dealing with the authorities, especially with the regulation. and Karen furnish the entrance. It's the wood. It's not the wood. Sorry. It's wastewater, and Karen have a wastewater plant just near the plant. So Gamma is the first additional demonstration project in France, currently under the plan, and commissioning schedule for late 2024, early 2025. What is in it? So I don't want, I will not describe the process, but what is important, it's the input must be pumpable. The capacity, it's a demonstrator, so it's a little capacity of gas injectable, about 1 megawatt hour for each hour. And at the difference of the gasification, we have minerals and metals in outputs, and water rich in nitrogen. And plant surface area on site is only 1,000 square meter. I like this slide because we can see many advantages for the thermal for the gazi for the gasification so strong reduction of final waste, conversion carbon very high, no atmospheric pollutant, production of methane-rich injectable gas, recovery and preservation of water, minerals, and nitrogen, and piping. Metal on heavy metal recovery, pre-conversion, compact and modular. As I said, it's only 1,000 square meter. High energy efficiency, and this technology allow to get rid of bacteria, viruses, and pathogen. Very favorable TIG and assessment environmental, and low odor and noise pollution. The last point is very important in the environment of the site for people to accept this kind of okay. And the last thing, what is very interesting with these three projects is the synergy. We can use, for example, waste heat for the thermal gasification to heat a product for the anaerobic digestion unit, for example. We can use the digestate from the digestion anaerobic unit to the thermal gasification, and we can share some equipment as a weight bridge. Okay. And the last thing I like to say that the Eco-Parc of Barillais has been awarded at the Green Solution Award, organized by Construction 21, and they have a website, and please have a look. It's very interesting. Thank you.
Thank you, Frédéric.
In view of time, if there is one quick question, I allow it. Very quick. Tilman.
Okay, my question is about the operation condition of the hydrothermal gasification. If it is a gasification, then temperature should be high, but then how can you produce methane?
The temperature is not higher than the thermal gasification, the classic gasification. The difference is that you have a solvent, and for hydrothermal gasification, the solvent is water.
Yeah, I know, but usually if it's gasification, then it should be 500 degree plus or something, and then it says you can have injectable gas, which means a lot of methane, which you don't get it above 500 degree.
So it's about the heat that we produce from the gasification process, what we do with the heat that we produce from the gasification process. This is the question.
equilibrium does not allow you to produce a lot of methane at above 500 degrees. So here it says on that slide, you have injectable gas. You produce somewhere methane, but how do you do that at 500 degrees?
Actually, you produce methane as in gasification. It's in a high temperature, but then you will cool it, but because you will do a methanation also. And that's, you have a methane that is in a condition of grid injection. So it's not really, and yes, the heat, you will recover it during the whole process.
It sounds like a perfect discussion for after the last two sessions. Okay, thank you. Our next speaker is Christian Wang. He's a senior consultant at EA Energy Analysis. He's online and he is working on Power to X and CCS. He's also involved in IEA Task 40 and co-lead of the IEA Bioenergy BECCS 2.0 Intertask project. So I would say the floor is yours. If you have control, then you can do it yourself. If not, then just shout out next slide, please.
Thank you very much. I'm trying to share my screen. Can you see my screen now?
Yeah, we see something and we hear you.
Okay, perfect. So let me go to, there we go. Are we in full screen mode here?
We don't see anything yet.
Lovely. Try again.
Yeah, now we see, it's not in presenting mode, but now we see your screen, the presentation. Yeah, now we see it.
Wonderful. Apologies for that. And there we go. Yes, thank you very much for the introduction. My name is Christian Bang from EA Energy Analysis, a Danish consulting firm. I'm regretting a little bit right now I'm not sitting there with you. It's about 12 degrees warmer down in Lyon, I can see. As you noted, I'm involved in Bioenergy's Task 40. I'm also the co-lead of the BECCS Phase 2 of the Intertask project. And most relevant for today, I've previously been involved with this Ørsted Kalundborg Hub project. So in this regard, I'd like to start by saying many thanks to Ørsted for providing inputs to my presentation today. Quickly, a little bit of background. I think you've probably touched on this a few times today, but internationally speaking, I think there's a growing consensus that if we're going to reach our international climate targets, some negative emissions are going to have to be part of that picture. And CCS is one of the main building blocks in delivering these negative emissions. In a Danish context, in 2020, the Danish Climate Act was adopted, which sets the long-term target of climate neutrality by 2050, and has a target in 2030 to reduce emissions by 70% relative to 1990. And this also meant that in 2020, the Danish state started to establish some different funds and mechanisms to encourage CCS, CCUS, and also negative emissions, as the 2030 target is actually quite reliant on the implementation of CCS. Here I'll focus on this particular, the first round of the CCS fund, which was launched by the Danish Energy Agency in 2022. There was roughly €1 billion set aside for this. And the objective was to encourage a project that could deliver 400,000 tons of CO2 emissions annually via the establishment of a CCS value chain. And this project had to be up and running by January 1st, 2026 as a minimum. And in May of this year, the winner of the first tender was announced as the DA awarded Ørsted a 20-year contract for its CCS project entitled Ørsted Kalundborg Hub, which is what I'll be speaking about a little bit today. quickly, just a little bit about Ørsted for those that may not be familiar. They develop, own, operate a number of energy assets, both within Europe and globally. They're a global leader in offshore wind. They have a strong presence in onshore renewables in the US and throughout Europe. They have a number of thermal power plants, primarily in Denmark. And they have an ambition in 2030 to be a global leader in renewable hydrogen and green fuels. If I just direct you to the Danish assets here, we have the Averø power plant on the eastern coast of Zealand. It's a CHP plant. And we also have the Esnes CHP plant on the west coast of Zealand. And these are the two assets that will be involved in this Ørsted Kalundborg Hub project. So again, if we zoom in on the two assets here, Averø and Esnes, and here you can see the dotted line depicts the route that the CO2 will be transported up to the west coast of Norway for sequestration and monitoring. Now, the four major partners in the project are Ørsted, and they'll be responsible for the entire CCS value chain. Construction of this has already started in June of this year, and they will be aiming to capture and store 430,000 tons of CO2 a year by 2026, with some of the first capture taking place in 2025. Now, the capture units, they're going to be delivered by Aker Carbon Capture. The transport, the sea transport, and the sequestration and monitoring will be undertaken by Northern Lights. And the off-taker for these negative emissions will be Microsoft, which is a large contributing in terms of the economics of the project. Yeah, okay, if we zoom in on the project a little bit more, we have the top of the diagram here. This is Averø-Værket. Averø-Værket actually has a number of different units, but the units that will have carbon capture applied to them is a straw-based unit. So there'll be two capture units applied to this, with the intention of capturing roughly 150,000 tons of CO2 a year. After capture, the CO2 is then compressed, liquefied, and then will be transported, at least initially, by truck across Zealand to the intermediate storage at the Esnes site. Here at Esnes, it's also a biomass-based unit. Here it's wood chips, and there'll be 3 capture units installed here, looking to capture roughly 280,000 tons of CO2 annually. The same, the compression and liquefaction, and then over into the intermediate storage. And this is where it's then handed off to the Northern Lights assets. Northern Lights will own and operate its own specially designed CO2 ships, which will sail up to the west coast of Norway, which will be transferred to their intermediate storage before it's sequestered underneath the seabed. I have another figure with that in a little more detail coming up here. Yeah, in terms of choice of technology, I mean, with having to be up and running fully by January 1st, 2026 is a very tight deadline, especially for one of the first of these large-scale projects. So there was a lot of emphasis placed on low-risk technical solutions. So the first aspect here is the carbon capture plant, which, as I mentioned, this comprises capture, compression, liquefaction, and intermediate storage. These last 3 components, compression, liquefaction, and intermediate storage, these are relatively widely deployed technologies. And as such, this wasn't really the core focus when selecting which technology to go with. It's the carbon capture units that are most complex and also require the most energy. So in this particular project, Ørsted decided on a standard modular technology based on amine absorption. And this was done for three primary reasons: to ensure certainty of cost, maintaining the timeline, and good performance. So if we turn to Northern Lights, here there's a little better illustration of their concept here with their ships, which will then deliver the CO2 to the receiving terminal, be stored here intermediately, and then piped 100 kilometers under the sea before it's then sequestered a little over 2.5 kilometers under the seabed for permanent storage and monitoring. And again, so why Northern Lights? Northern Lights, or Norway, has been safely storing CO2 deep in the North Sea for over 2 decades. And Northern Lights is actually part of the Norwegian government's full-scale carbon capture and storage project, the Longship. And also particularly relevant here is that the storage complex known as Aurora is meant to start operations in 2024, therefore giving Ørsted a good buffer in terms of the first captured volumes coming from Ørsted in 2025 and full-scale implementation in 2026. And lastly, and definitely not least important, is the fact that Northern Lights has a lot of focus on monitoring, both during transport, during injection, and also post-injection, to ensure that there's no leakage and that the CO2 is being permanently stored in the desired fashion. And then last, and again, certainly not least, a very, very important aspect of this project is the fact that the CO2 emissions that are being captured are biogenic in origin. It's residue biomass that's used in both of the power plants. So this means that they will create negative emissions, and these negative emissions can be converted into high-quality carbon removal certificates. Again, this was a focus of interest for Ørsted. They wanted very high-quality, top-of-shelf removal certificates, and this was something that the Danish Energy Agency was interested in. This is something that the Microsoft is interested in. And to ensure this, they'll be certified according to internationally recognized standards. In fact, the project has been chosen as a pilot project for the first CCS certification of BECCS projects. And also tied to this, and this is again, the DA had some very stringent criteria for this in the material, is a very comprehensive MRV, that is monitoring, reporting, and verification system has to be in place. And this is something that Ørsted's been working a lot with and will continue to work with throughout the course of the project. So to summarize their approach to carbon removal certificates, essentially it's the certified, they have to be certified according to recognized standards. They can only count once towards global emissions. They must deliver additional climate action, and they should only be utilized after all other climate action has been undertaken. Yeah, so for a little bit more information on the project, you can visit Ørsted's website. They also have a nice video there and some more details on the project.
Okay, thank you, Christian. So again, in view of time, I will allow one question, but we have to go to the final speaker. So if there is a question. Yes, Peter.
Thank you for an interesting talk on an interesting project. I wondered, do the carbon certificates the project will receive subtract the LCA carbon in generating the CO2 for injection? So the transport, fuel use, etc., etc.
What I can say is that in terms of the counting for the Danish Energy Agency, they don't look at LCA. I can't really get into the details of the agreement between Microsoft and Ørsted, but I'm sure the LCA is something that they're looking at. So I'm sorry for the non-response.
Well, sometimes that's it. It is what it is. Okay, thank you, Christian. We will now go to our final speaker. which is Jean-Philippe Héraud. He's from IFPEN, Energie Nouvelle. He's working on advanced biofuels and the head of the Fischer-Tropsch and the biofuel projects for IFPEN. And the floor is yours.
Thank you for the invitation. I will be the last, so I will try on. I think we are a little bit late, so I will try to speed up my presentation. This afternoon, Aisha said that we have It's okay? Okay. Sorry. So Aisha showed this afternoon that we have a potential problem of CO2 resources for the e-fuel application. So I will try to explain how advanced biofuel can be a solution to produce this CO2 and the synergy we have between the different way. So just one word about IFP Energie Nouvelle. It's a public institute dedicated to research and innovation on an industrial group. On this industrial group put on the market our research. This is the eye of innovation. We are about 1,000 people dedicated to research on energy, transport, and environment. So we consider today that in 2030 we have more or less 4 main pathways for the production of sustainable aviation fuel. The first one is about hydrogenated vegetable oil. So for sustainable aviation fuel, we are speaking about used cooking oil on animal fat, mainly. The second way is the biomass to liquid or the e-biomass to liquid. I will make a focus on this way at the end of the presentation. The third one is alcohol to jet, mainly ethanol. So we are producing ethanol, and after we have the conversion of ethanol into jet. On the last way, it's e-fuel. This way could be considered like a little bit less in time of market time in order to produce some e-fuel. I will focus mainly in the third way, the ethanol production. So just a sample scheme to explain you what is the production of ethanol from lignocellulosic biomass. After a kind of pretreatment, you are making hydrolysis and fermentation. The hydrolysis is done by enzymes. On this enzyme, we take the sugar, the different sugar you have in the biomass, and after that, the yeast will make the fermentation of this sugar to produce many products, ethanol, CO2, and also lignin, which is a biomass product. This is not only ethanol, it's an energetic hub as you are producing many products. Let's put some figures on this scheme. I take some roof example. We are considering a unit of 150 kilotons per year of biomass, and considering a mass yield of 20%, which was estimate for the mass yield, we are producing 30 kilotons of ethanol. And if I go back, I said that the ethanol is produced by fermentation of sugar. So if I take the right chemical reaction of sugar for production of ethanol from sugar, we are seeing that we are producing 2 moles of ethanol and 2 moles of CO2. So that means we have the same amount in terms of mass produced on CO2. So you have 30 kilotons per year of ethanol, or we have about 30 kilotons per year of CO2. This CO2 is mainly used for e-fuel production, and is really a kind of sources. I just made a quick scheme about the e-fuel. So we are taking the CO2, atmospheric, biogenic or fossil CO2. Before we have biogenic CO2, which is the CO2 which is more interesting for us in the next years. If we are going from atmospheric, from industrial, it's necessary to make CO2 capture. And with this CO2, we mix with hydrogen and we make a reverse water gas shift in order to produce a syngas. And after the syngas, we can make Fischer-Tropsch synthesis. I take this example of Fischer-Tropsch synthesis. You can make other products with the syngas, just for the example and to explain you the link we can have between ethanol and e-fuel units. I take the same amount of CO2 we are producing by the ethanol units, so about 30 kilotons per year, and I make the same, a quick mass balance on the reaction to produce a sustainable aviation fuel. I take a molecule with 12 carbon number, and what we can say, I consider 100% reaction on, okay, just to have some order of magnitude on the roof estimation, based on the 30 kilotons per year of this CO2, we are able to produce about 11 kilotons per year of sustainable aviation fuel. So 1/3 of the CO2 we are entering in the process, you are producing SAF. For that, you need some hydrogen. The same reaction says that we have need about 4 kilotons per year of hydrogen, which is about 200 gigawatts per year, water per year of electricity, renewable electricity. So I make the combination of ethanol and e-fuel just to synthesize the two pathways. The first one, if you are producing only ethanol, we are a mass yield of about 20%, so an energy yield about 37%. I put weight is to that true. If I use this CO2, which is a byproduct or which is not used for ethanol units, we're able to increase the production of product of interest. In this case, I put sustainable aviation fuel as an example, and we are increasing the mass yield. The mass yield is based on the linoselic biomass we are introducing on the unit to 27%, so 7% more of product. And the energy yield is about 45%. I take account the electricity we need for the e-fuel pathway. So it's e-fuel electricity and linoselic biomass energy content. Another example is not exactly the same as the integration between the two processes, but it could be think about like this. I take the BTL pathway, and from BTL pathway, I take the same. The order of magnitude is 20% of carbon mass yield. So for the production of 30 kilotons per year, we use about 150 kilotons of linoselic biomass. But in this reaction, we need to make an adjustment of the ratio hydrogen to CO for the Fischer-Tropsch reaction. And we pass from 0.6 to 2, 0.6 at the outlet of the gasifier, and to 2 to the inlet of the Fischer-Tropsch. For this purpose, we need to put a water gas shift unit. So we are using CO with water in order to produce hydrogen to increase this ratio. But the counter effect is that we are producing also CO2. And the amount of CO2 is about 115 kilotons per year. So you can say, okay, I will use the CO2 and I will put the same as ethanol, and I will make an e-fuel unit. But if I make an e-fuel unit, I will make a river water gas shift. I need an electrolyzer, and I need also a Fischer-Tropsch unit, but I can have this Fischer-Tropsch unit with this unit. So it's not the main point. What could be done is to avoid to produce this CO2. And how we can make to avoid to produce this CO2? We can adjust this ratio directly putting hydrogen in the unit. So we'll have the electrolyzer. We'll put some directly hydrogen, about 11 kilotons per year, in the syngas coming from the biomass. We will increase the ratio from 0.6 to 2. In this case, we are doubling the production of product because we are using all the carbon or maximizing the carbon biogenic content in the biomass in the final product. So it's not exactly a way to use CO2 from the BTL unit, but it's a way to avoid CO2 and to maximize the production of sustainable aviation fuel. So it's also interesting to see how we can make integration of the different process and how we can use the process to use the maximum carbon content of biomass. So this is my last slide. So we have different pathways for producing advanced biofuel. I explained some, but if you are looking hydrogenation of vegetable oil, you can also have synergy and integration between this process and e-fuel process. We are ready for deployment. So when we have the unit in operation in the next 5 years, I want to say we are able to make this kind of integration at industrial scale. advanced biofuel is a source of biogenic CO2, and we need to have this CO2 in order to address the amount of sustainable aviation fuel. I take only this example required by the regulation. We need to integrate the different process, so which is very important. And when you have the know-how of the different process, you can do that. So it's very important. I make only an example about CO2, but at the first, we said before, we can make also integration between different other streams on the unit in order to reduce the capex, to reduce the opex, and to use at the maximum to increase the energy yield, in fact, of the process.
Thank you. Very interesting presentation. I guess there are some questions about this.
So clear.
It was clear, yes. Yes, Luc.
Thank you. Very interesting initiatives also. Do you know already something about the economics of introducing hydrogen in the process? And is it worth the extra yield that you have at the end to do that? So how does it come out in the business case for you?
The cost of hydrogen is the cost of electricity, depending on the different scenario. The main, which is important, is there is 2 points. You need to keep the life cycle assessment, which is very important. So you need to have renewable energy. And for the increasing of liquid product at the end, for example, it's something very sensitive in terms of economics. And for sure, hydrogen is important in the OPEX, but it's manageable. And some new development of hydrogen production to reduce the cost are also is attended in the next years. Yeah.
Okay, thank you. Is there a question online?
Yes, please. Have you considered to produce bioolefins? For example, biomass, methanol, olefins.
It's I take the example of Fischer-Tropsch for just to illustrate the purpose and the possible integration. For sure, you can have also way in order to valorize the CO2. Here we know that for some specific sectors, we need to have some product, and it's very difficult to decarbonize some areas like aviation of maritime. And with this kind of product, you are able to do that. So that's why I just illustrate my presentation by the integration between ethanol and Fischer-Tropsch.
Thank you.
Okay. Thank you. Then I will hand over to Luc Pelkmans, who is, well, he has the honor to summarize the entire day.
Thank you. Okay, considering the time, so the reception, there is a reception at 5:15, so it means I have 4 minutes to make the summary, which is not that bad. So I keep the summary very, very short. So first of all, I would like to thank everybody, the speakers, the panelists, the moderators in the first place, also the audience here, also for your active participation, and the audience online. I hope there's still many people online. We will have a check afterwards how many we had, but I think it was around 200 people. So I think that's also great. And a special thanks also to ADEME for hosting us here and for organizing this. It's really appreciated, our help. Many thanks for helping us out. To start, one practical thing, the slides and the recordings of this workshop, I realized it was a far away till the end of the room here to see all the small things. So the slides of all the presenters where we get permission will be put on the website, normally early next week. And also the recordings, I will have to check with the IT people, but normally the recordings will also be available. Just about today, so we had the morning session, which was a bit more on strategies, on how we see the long-term role of biomass and bioenergy, which according to IEA is quite important in the whole energy system. But you also have to look at not just the global scale and then looking at top down, but also looking at what's regional. So all the regional specificities, the local specificities are pretty important in that. And I think agriculture, it has mentioned that I think for the presentation from France also that a lot is expected from agriculture. There may be an interference also with climate change impacts in the next decennia. So I think that's all things to be taken into account. The afternoon, very short, we talked about concepts, developments that we see in the area, and we see quite a lot actually happening on, well, we put a lot of focus on CO2, on the carbon efficiency. That's where we see a lot of movement of really getting the most out of the carbon that we have from the biomass, because biomass is carbon and we want to actually get rid of the fossil carbon, so we have to use it best as possible. There's also something I need to say from the morning session, that this hierarchy, so priority, difficult words after the afternoon, prioritization, merit order. So these are things that we need to think of, and how can we deal with this in policies. But it also comes back in the afternoon in the concepts that you see appearing, that really the sectors where you need, where it's difficult to decarbonize, that you need to focus more on that apparently. The value of carbon and CO2, I think there's tremendous things we can do. Either we convert it to negative emissions, either we put it in carbon capture and utilization and making e-fuels, e-products, all kinds of it together with hydrogen, where we have to also be careful that, well, of course, hydrogen in many cases also means a lot of renewable electricity, and yeah, that will also be limited, even though there will still be some growth. And biohydrogen can also be an important, an interesting concept, certainly in some cases. Gasification came up also. I think the last section was a bit more focused on gasification. Don't forget other options. So this session was a bit focusing on gasification, but it's an interesting technology in terms of flexibility from the input side and flexibility on the output side. And you can steer that actually to the sectors and the products that you would need. And this can be dynamic in time also, that in the longer term you can steer it to specific products.